A spacecraft launched before most of you were born, just crossed the edge of our solar system, and what it found out there broke nearly every model scientists had built. The boundary was denser, hotter, and stranger than anyone predicted. We will travel from the moment Voyager left Earth, through the invisible wall of solar wind, past the churning foam at the edge, and into true interstellar space. If you enjoy the journey, like and subscribe. It keeps us going. Now brace yourself. We begin. 1977. The Cold War is at full pressure. America and the Soviet Union are racing through space, and inside a NASA control room in California, a team of engineers is preparing to do something that had never been attempted: send a machine to the outer planets using gravity itself as the engine. Voyager 1 lifted off on September 5, 1977, 16 days after its twin, Voyager 2, which launched first on a slower path. The plan was straightforward: visit Jupiter, visit Saturn, take pictures, send data, end of mission. Nobody in that room was planning for interstellar space. The rocket that carried Voyager 1 was powerful, but raw thrust alone could never have sent it where it ended up. What made the mission possible was a rare alignment of the outer planets that only repeats once every 175 years. Jupiter, Saturn, Uranus, and Neptune lined up in a curved arc that allowed a spacecraft to slingshot from one to the next, stealing a fraction of each planet's orbital energy. Scientists called it the Grand Tour trajectory. Without it, reaching the outer solar system would have taken decades longer, and the probe would have needed fuel we could not carry. Think of it like a ball rolling into a spinning carousel. If the timing is right, the ball gets flung outward faster than it came in. Voyager 1 did that 4 times over. Each gravity assist, added speed. Jupiter alone accelerated the probe by roughly 35,000 miles per hour. Saturn added more. By the time Voyager 1 cleared the outer planets, it was the fastest human-made object ever built. And it was still accelerating. Here is what most people do not realize. Voyager 1 was never supposed to keep going after Saturn. The mission plan ended there. Saturn's moon Titan was the final scientific target. Scientists wanted a close flyby, and getting it required tilting the spacecraft's path sharply upward, out of the plane where all the planets orbit. That tilt ruled out any further planet visits. Voyager 1 was flung away from the solar system at an angle, heading toward empty space. Engineers knew this when they made the choice. They chose Titan anyway. And that decision, made in the late 1970s, is the reason Voyager 1 became the first human machine to cross into interstellar space. But here is what nobody told you about that moment of launch. The spacecraft carried a golden record, a 12-inch gold-plated copper disc containing sounds and images from Earth. Music, languages, greetings, the sound of rain, a mother's first words to her child. It was placed there in case something somewhere ever found the probe. Carl Sagan helped design it. Scientists at the time described it as a message in a bottle thrown into a cosmic ocean. The ocean they were throwing it into turned out to be stranger than any of them imagined. Voyager 1 left Earth carrying instruments built to measure planetary atmospheres, magnetic fields, and radiation belts. Its cameras were pointed at gas giants and their moons. The entire spacecraft was engineered for a known environment, for a solar system that scientists thought they understood. But the universe had a different plan. Within years of Saturn's flyby, mission scientists noticed something unexpected in the data. A small but persistent force was nudging Voyager 1 off its predicted course. The math said it should be in one place. The signal said it was somewhere else. The gap was tiny. But it was real, and nobody had an explanation. That mystery would take decades to solve. And solving it would force scientists to completely rethink what exists between us and the stars. What waits just beyond our solar system turned out to be one of the most surprising environments ever measured, and Voyager 1 was the only machine alive to report back from it. Saturn's rings filled the cameras in November 1980. Voyager 1 swept within 77,000 miles of the planet's cloud tops and captured images so sharp they rewrote textbooks overnight. Scientists could see individual ringlets, storm systems, shadow patterns cast by moons onto the gas below. Then it kept going. The cameras eventually powered down to save energy, the planetary instruments went quiet, one by one, and a spacecraft designed for a 2-year mission entered the 3rd year, then the 5th, then the 10th. Nobody shut it off. The reason is both simple and extraordinary. Voyager 1 kept working. Its nuclear power source, a set of small radioactive generators that convert heat from decaying plutonium into electricity, kept producing power. The instruments that survived the planetary flybys continued sending data, and that data, even from the empty space beyond Saturn, was scientifically valuable in ways that the original mission designers had not fully anticipated. Scientists began to realize something important. Voyager 1 was heading into a region no probe had ever entered, a zone between the warm bubble our star creates and the raw interstellar medium beyond. Nobody knew what was out there. The probe's surviving instruments, its low-energy charged particle detector, its magnetic field sensor, its plasma wave instrument, happened to be exactly the right tools to measure it. So the mission extended, then extended again, and again. By the time Voyager 1 reached the edge of the planetary zone, it had been traveling for over a decade and a half, and it had not missed a single day of transmission. Every 6 hours, a signal traveling at the speed of light crossed hundreds of millions of miles and arrived at NASA's Deep Space Network antennas. Engineers on the ground received whispers from a machine older than the internet, running software that would not fit on a modern smartphone. What kept scientists watching was a growing suspicion. The space beyond the planets was not truly empty. Something was out there, something with boundaries, with structure, with physical properties that could be measured if you had an instrument in the right place at the right time. Voyager 1 was the only instrument in the right place. Here is a detail that feels almost impossible. The probe runs on roughly enough electricity to power a single refrigerator light bulb. The signal it sends back, crossing billions of miles of vacuum, arrives at Earth with less power than a snowflake landing on your hand. Yet scientists can still read it. The antennas catching that signal are so sensitive they can detect energy levels 1 billion times smaller than what it takes to light a single LED. The mission extended through the 1980s and 90s because the science kept getting richer. But what truly changed everything came in the early 2000s, when Voyager 1's instruments began measuring something that planetary scientists had never seen before. The data shifted. Particle counts changed. Magnetic readings behaved differently. The probe was entering a new environment, and the transition was unlike anything the models predicted. Scientists had spent decades building theoretical models of what the edge of our solar system should look like. Clean, structured, predictable. Every one of those models was about to be wrong. The instruments were still transmitting. The data was still flowing. And the picture forming from that data was one that nobody in 1977 could have imagined when they bolted those golden generators onto the side of a spacecraft and pointed it towards Saturn. Something enormous and invisible surrounds our solar system, and Voyager 1 was about to drive straight into its wall. Before Voyager 1 reached the edge, scientists had a theory, a confident one, built over decades of calculation, observation, and model building. They believed the outer boundary of our solar system was a clean, well-defined shell, a point where our star's influence simply stopped and the emptiness of interstellar space began. The picture in most textbooks looked orderly. Our star pumps out a constant stream of charged particles in every direction. That stream, called the solar wind, travels outward at roughly 1 million miles per hour. At some point far beyond the planets, scientists calculated that wind would slow down, thin out, and stop. The transition would be relatively smooth, a predictable fade from our solar neighborhood into the void beyond. They were wrong. Profoundly, fascinatingly wrong. The first hint of trouble came from the models themselves. Scientists had built their predictions using measurements from the inner solar system, data from satellites orbiting Earth, instruments on spacecraft near Mars and Jupiter. They extrapolated outward, assuming the behavior of solar wind would scale predictably with distance. But space does not always cooperate with clean extrapolation. What those models missed was the dynamic nature of the boundary. Our star does not blow a perfectly round, perfectly steady bubble. It pulses, it surges. Coronal mass ejections, massive eruptions of plasma from the stellar surface, send pressure waves outward, Solar activity rises and falls over an 11-year cycle, making the wind stronger or weaker depending on the decade. The boundary between our solar system and interstellar space moves, it breathes. Scientists expected a fixed wall. The reality was a living membrane. And here is where it gets genuinely strange. The interstellar medium, the thin gas and magnetic field that fills the galaxy outside our solar system, pushes back. There is pressure from outside. Clouds of charged particles drifting through the galaxy collide with our star's outward stream. The boundary between those two forces is shaped by both sides simultaneously, and neither side holds perfectly still. The result, as Voyager 1 would eventually confirm, is an edge region with far more structure than anyone predicted. Layers within layers, magnetic features, particle highways, a churning zone that looked nothing like the clean model in the textbooks. But in the 1980s and early 90s, none of that was confirmed yet. It was theory. Competing papers argued over the shape of the boundary, its distance from our star, its thickness, its behavior. Some scientists thought Voyager 1 would cross it in under a decade. Others said it would take 30 years. The debate stretched across careers, and underneath all of it was a question nobody wanted to say out loud. What if the boundary is so different from our models that we will not even recognize it when we cross it? That turned out to be almost exactly what happened. When Voyager 1 finally reached the edge region, the data it sent back did not match the predicted picture. The instruments reported conditions that forced scientists to go back to their models and ask a harder question: how much of what we thought we knew about our own solar system was actually just assumption? The answer was uncomfortable. The clean edge was gone. In its place was something far stranger, and the first layer of that strangeness had a name that sounds almost peaceful. It was anything but. Picture a candle burning in the middle of a windstorm. The flame pushes air outward in every direction, but the storm pushes back. Around the candle there forms a protected zone, a region where the candle's own breath holds back the wind. Step outside that zone, and the full force of the storm hits you. Our solar system lives inside something like that protected zone. Our star constantly exhales. Every second, it releases a stream of charged particles, electrons and protons mostly, moving outward at speeds of up to 1 million miles per hour. This stream flows in every direction simultaneously, filling a vast sphere centered on our star. Scientists call it the solar wind, and it has been blowing continuously for over 4 billion years. The region that solar wind fills and dominates is called the heliosphere. Every planet in our solar system, every moon, every asteroid, every comet closer than the far outer edge, sits inside this bubble. Earth is inside it. Mars is inside it. Even the distant gas giants float within the heliosphere's boundaries. The heliosphere is enormous beyond comfortable imagination. Its outer edge, where solar wind finally loses its battle against interstellar pressure, sits somewhere between 11 billion and 14 billion miles from our star. Voyager 1, traveling at roughly 38,000 miles per hour, took over 35 years to reach it. 35 years of constant travel to cross one bubble. But here is what makes the heliosphere more than just a size story. It is a shield. As Voyager 1's data eventually confirmed, the heliosphere deflects a significant portion of the high-energy cosmic rays streaming in from the rest of the galaxy. These cosmic rays are particles accelerated to near-light speeds by supernovas, black holes, and other violent galactic events. Left unchecked, a flood of them would reach Earth's surface. The heliosphere absorbs and deflects a large fraction of that bombardment before it ever gets close. Life on Earth exists partly because of this bubble. Scientists have theorized the heliosphere's existence since the 1950s. A physicist named Eugene Parker predicted the solar wind itself in 1958, and the broader bubble it creates followed logically from that prediction. But predicting something and measuring it are very different things. For decades, the heliosphere was a mathematical object, a region defined on paper by equations, visible only indirectly through the behavior of comets and the faint glow at the solar system's edge. Voyager 1 would eventually turn it into something measured, confirmed, and far stranger than the equations suggested. What scientists did not fully appreciate until Voyager 1 sent back data from the outer heliosphere is how dynamic the interior of the bubble truly is. Close to our star, solar wind flows outward fast and smooth, like water rushing from a tap. But farther out, pressure builds. The wind piles up against the resistance of interstellar space, and at a certain distance, the flow does something dramatic. It hits a wall. A wall that Voyager 1 crossed in 2004, and the crossing produced data so unexpected that scientists spent years arguing about what they had actually measured. The wall had a name, and what happened when solar wind crashed into it was unlike anything in the original models. Voyager 1 was engineered for a specific job. It carried instruments designed to measure known things in known environments: magnetic fields around gas giants, plasma clouds surrounding planetary moons, radiation belts similar to the ones wrapped around Earth. The science team built their tools around what they expected to find, because that is how you design a spacecraft. You do not pack instruments for places you have never imagined going. By 1981, after the Saturn flyby, that job was done. The cameras had captured their images, the planetary instruments had collected their data, and a spacecraft full of tools designed for a specific environment was now flying into something completely different. What kept it scientifically useful was a combination of luck and foresight. Several instruments aboard Voyager 1 happened to be exactly right for measuring interstellar boundary conditions, even though that was never their primary purpose. The low-energy charged particle detector, built to measure radiation around planetary systems, turned out to be sensitive enough to track subtle shifts in particle flux across billions of miles. The magnetometer, designed to map the magnetic envelopes of gas giants, remained accurate and functional well into the probe's journey through the outer solar system. The plasma wave instrument, meant to listen to electromagnetic noise in planetary environments, began picking up entirely new sounds in the outer reaches of the heliosphere. A team of scientists who had spent their careers studying Jupiter and Saturn suddenly found themselves in a completely new field. They were measuring something nobody had a full theory for. Every data point from the outer heliosphere was, in a sense, the first data point of its kind. Here is what made their job particularly strange. There was no reference point. When you study a planet, you can compare your data against every other mission that visited it. You can cross-check. You can validate. In the outer heliosphere, Voyager 1 was completely alone. No other spacecraft had ever operated there. Every reading was original. Every anomaly was a genuine unknown. And the anomalies started early. One of the first things scientists noticed, even before Voyager 1 reached the outer boundary, was that the density of cosmic rays gradually increasing as the probe moved outward. Each year, farther from our star, the count of high-energy particles from outside the solar system ticked slightly higher. The heliosphere was doing its shielding work closer in, but as Voyager 1 pushed beyond the outer planets, the shielding got thinner. The galaxy was leaking in. That was expected, broadly. What came next was not. In the early 2000s, Voyager 1's instruments began registering a shift in particle behavior that did not fit any existing model. The charged particles measured by the probe seemed to be moving differently, following structures in the magnetic field that had no business being there, according to standard theory. Scientists called a meeting, then another. The data kept arriving, whispered across 11 billion miles of vacuum, at the speed of light, arriving at Earth so faint that only the most sensitive antennas on the planet could catch it. What those antennas were receiving was the first evidence of a boundary layer so complex that it would take a decade of argument to fully understand. And the probe measuring it was running on the power of a dim light bulb, held together by software written before most of its scientists were born. The journey into the unknown had begun years before anyone realized it. Sometime in the 1980s, engineers at NASA's Jet Propulsion Laboratory noticed something small and deeply troubling. Voyager 1 was not where it was supposed to be. The discrepancy was tiny, a fraction of its total distance traveled. But the navigation team knew exactly where the probe should be based on every known force acting on it, the gravity of the planets it had passed, the push from the rockets it had fired, the gentle but measurable pressure of sunlight against its body. They had modeled everything, calculated everything, and still, the probe kept drifting slightly off the predicted path. They called it the Pioneer Anomaly because the Pioneer 10 and Pioneer 11 spacecraft showed the same thing. Both Pioneers, flying on their own paths out of the solar system, were being nudged toward our star by a tiny but persistent force, a force that existing physics could not explain. For years, this was a genuine crisis in spacecraft navigation. If something unknown was pulling on probes in deep space, then every mission calculation, every trajectory model, every future deep space navigation plan carried an invisible error. The size of that error was small, but small errors compound over billions of miles. Scientists proposed explanations ranging from new physics to undiscovered matter. Some researchers quietly wondered if the standard model of gravity itself was slightly wrong at interstellar distances. Papers were published, debates ran for years. The anomaly became one of the most discussed unsolved problems in space science. Then, in 2012, a team found the answer. And it was humbling. The Pioneer spacecraft were not perfectly symmetric. Heat leaked from their power systems, from their electronics, from their nuclear generators, unevenly. That heat, radiating into space, produced an almost immeasurably small thrust, like a jet with a leak so tiny you can barely feel it, but real. Over decades of travel, that tiny thermal push accumulated into a measurable drift. The anomaly was real. The force was heat. Voyager 1 was slightly different in design, and therefore showed a smaller version of the same effect. But what this episode revealed was more important than the explanation itself. It showed how honest scientists had to be about what they did not know. For over 20 years, a real unexplained force existed in the solar system's outer reaches, and nobody could explain it. The solution turned out to be engineering, not exotic physics. But the process of getting there forced an entire generation of researchers to interrogate their assumptions at every level. And that habit of interrogating assumptions was about to become essential. Because even as the Pioneer anomaly was being resolved, Voyager 1's instruments were picking up something else, something bigger, a shift in the particle environment around the probe that had nothing to do with heat or thrust or navigation. The solar wind was changing. The behavior of charged particles around the probe was shifting in a way that suggested Voyager 1 was approaching something massive and structural, a boundary, a physical transition zone in space. And on the other side of that zone, everything the instruments measured would be different. The probe was closing in on the wall, and the wall, when it finally showed up in the data, looked nothing like the clean edge in the models. Before Voyager 1 reached the outer boundary of the heliosphere, something strange happened to its data. The particle counts changed. Low-energy particles from our star started dropping. Cosmic rays from outside the solar system started rising. The magnetic field the probe flew through began behaving erratically. And buried inside all of that, a pattern emerged that made scientists stop and stare. The particles were not just rising and falling randomly. They were moving in pulses, waves, as if something far larger than the probe was rhythmically pushing and pulling at the environment around it. The solar wind was not fading smoothly the way the models said it should. It was compressing, heating, and doing something that had no clean name in the existing scientific vocabulary. For several years in the early 2000s, a quiet argument ran through the Voyager science team. Some members believed the probe had already crossed the outer boundary. Others said the data showed it was still inside. The instruments were reading conditions nobody had ever seen before, and there was no textbook for it. Here is why this mattered beyond the immediate science. Everything we had built, every calculation about what the edge of the solar system looks like, every model of how our star interacts with the galaxy around it, rested on assumptions that had never been tested with actual measurements. The Voyager data was the first real test, and the test was failing the models. One specific reading haunted the science team. The probe was measuring the direction of the magnetic field lines in the outer heliosphere. According to the prevailing theory, those field lines should have been running in one consistent direction, curving outward with the solar wind. Instead, they fluctuated. They bent in unexpected ways. They seemed to be responding to something outside the solar system, pressing inward from multiple directions at once. Scientists call the region where solar wind begins to slow and compress the heliosheath. They expected it to be thin, a transition zone you could cross in a year or two. Instead, Voyager 1 flew through it for nearly a decade. A decade of churning, compressed plasma. A decade of magnetic chaos. A decade of readings that forced model after model to be revised and discarded. During this entire period, the probe was transmitting continuously. Every 6 hours, a signal crossed billions of miles at the speed of light and arrived at Earth weaker than a whisper in a thunderstorm. 70-foot antennas had to be pointed with extreme precision to catch it. The scientists who read that data knew they were receiving something no instrument had ever measured from this close to the edge. And every reading made the edge more complicated. The force that nobody could name turned out to be something more fundamental than a single anomaly. It was the combined pressure of two cosmic environments fighting for dominance. Our star's breath pushing outward, the galaxy's ambient pressure pushing inward. The result was a boundary zone so turbulent, so layered, and so thick that crossing it took the fastest human-made object ever built nearly a decade. But inside that chaos, something else was hiding. A structure so specific and so unexpected that when Voyager 1's instruments finally detected it, scientists compared the discovery to finding a road in the middle of the wilderness, a highway in the magnetic field, organized, directed, and completely unexplained. Every second of every day, our star is losing mass, not slowly, in the way stars gradually age and shrink, explosively, continuously. A stream of charged particles tears free from the stellar surface, accelerates outward, and spreads in every direction simultaneously at speeds between 300 and 700 miles per second. This is the solar wind, and it shapes the environment of every planet in the solar system, including Earth. The solar wind carries two main ingredients, protons and electrons, stripped hydrogen atoms and their lost partners, flying outward as a plasma. Plasma is the fourth state of matter, beyond solid, liquid, and gas. It is a superheated soup where particles move so fast they cannot hold their atomic structure together. The entire flow is magnetized, threaded through with field lines that spiral outward from our star, like water from a spinning garden sprinkler. By the time the solar wind reaches Earth, roughly 93 million miles from its source, it is still moving at around 1 million miles per hour. Earth's own magnetic field deflects most of it, pushing it around the planet like a river splitting around a stone. Some particles leak through near the poles, and those create the aurora. But the solar wind does not stop at Earth. It keeps going, through the asteroid belt, past Mars, past Jupiter and Saturn, out through the realm of Uranus and Neptune. And still it keeps going, thinning with distance but never truly stopping until it meets something strong enough to push back. That pushback happens somewhere between 11 billion and 14 billion miles from our star. At that distance, the solar wind has spread so thin and slowed so much that the pressure from interstellar space finally overpowers it. Voyager 1 crossed that region, and what it measured there told scientists something they had not expected. The solar wind does not fade quietly. It crashes. Think of a supersonic jet crossing the sound barrier. As the jet accelerates past the speed of sound, a shockwave forms in front of it, a compressed wall of air that the jet plows through. The solar wind does something almost identical at its outer boundary, moving faster than the speed of sound in the surrounding plasma. The wind eventually hits the resistance of interstellar space and slams into a shockwave of its own creation. Scientists call this the termination shock, and Voyager 1 crossed it in 2004. The crossing lasted months. The probe did not punch through a clean wall. It drifted in and out as the boundary pulsed and flexed, pushed inward by gusts of interstellar pressure, then relaxing outward again. 3 times, the instruments recorded conditions that suggested a crossing. 3 times, the probe appeared to exit and re-enter the shock zone before finally clearing it for good. The data from inside the termination shock was startling. Particles that had been flowing smoothly outward suddenly slowed and heated dramatically. Temperatures in the shocked plasma rose to levels that broke the models. The magnetic field compressed and tangled. Scientists had predicted this crossing broadly. What they had not predicted was what waited on the other side. The termination shock was just the first wall. Beyond it, a new environment began, strange, thick, and full of structures nobody had imagined. and Voyager 1 was about to spend a decade inside it. On December 16, 2004, Voyager 1 crossed a boundary that exists at the edge of our star's direct influence. The moment had been anticipated for years. Scientists had debated the exact location of the termination shock since the 1970s, building models, revising estimates, arguing over whether Voyager 1 would reach it before its instruments failed. When the crossing finally came, it arrived in the data as a sudden, sharp shift. Particle counts jumped, the magnetic field compressed, and the solar wind, which had been flowing outward for 11 billion miles, effectively stopped. Stopped is the right word. The solar wind does not actually cease to exist at the termination shock. The particles are still there, but their organized outward flow, their directionality, collapses. Inside the shock, the wind was supersonic, moving faster than any wave could travel through the surrounding plasma. At the termination shock, it slows below that threshold and becomes something chaotic and pressurized, like steam hitting a cold surface and billowing in every direction. Here is the comparison that makes it visceral. Imagine you are standing under a waterfall so powerful that the water falls faster than sound. The moment that water hits the pool below, it does not gently spread. It explodes outward, creates foam, creates pressure waves, creates turbulence that rolls in every direction. The termination shock is the pool. The solar wind is the waterfall. What Voyager 1 measured inside that zone was deeply strange. Particles that had been flowing at predictable energies suddenly showed a completely different energy distribution. Some were accelerated dramatically by the shock itself, a process called diffusive shock acceleration. High-energy particles ricocheted back and forth across the shock boundary, gaining energy with each crossing, like a pinball bouncing between paddles. This was theoretically predicted. Scientists had known shock acceleration should happen at the termination shock, but the actual numbers, the specific energies and particle ratios, came out wrong. The shock was accelerating particles less efficiently than the models said it should. Something else must be doing part of the job. That something else took years to identify. Meanwhile, the magnetic field at the termination shock behaved in a way that troubled field theorists. The field compressed significantly, as expected, but the direction it compressed into did not match the prevailing model. The field lines tilted. They folded. They pointed in directions that required a complete rethinking of how our star's magnetic influence interacts with the interstellar environment at large scales. 3 separate research groups published conflicting interpretations of the termination shock crossing data within 18 months of the event. The debate over what Voyager 1 actually measured at the shock boundary lasted years. Papers argued over particle acceleration rates, over magnetic field geometry, over the thickness of the shock itself. All of that arguing was productive. It forced the field to confront how much of the standard heliospheric model was guesswork, extended beyond its valid range. And here is the thing. The termination shock, for all its chaos and complexity, was only the doorway. Beyond it stretched a region that would be even harder to explain. A thick, churning layer that took nearly a decade to cross and delivered data that shook the foundations of space plasma physics. The real surprises were still ahead. When the termination shock crossing data came back to Earth, the scientists who had spent decades waiting for it gathered around their screens and read the numbers carefully. Then they read them again. The data did not match the predictions. Specifically, it did not match in 2 ways that immediately demanded explanation. First, the temperature of the plasma inside and beyond the termination shock was far higher than expected. Models had predicted that the solar wind, upon slowing and compressing at the shock boundary, would heat to a specific temperature range. The actual reading was several times higher than that range. The extra heat had to come from somewhere. Energy does not appear from nothing. Something was pumping additional energy into the plasma at the shock boundary, and nobody had accounted for it. The leading candidate was a category of particles called anomalous cosmic rays. These are low-energy particles from interstellar space that get swept up by the solar wind and carried inward, then flung back out and accelerated at the termination shock. Scientists had expected them to be accelerated at a specific rate. Instead, their energy distribution looked completely different from the theoretical prediction. The implication was significant. The termination shock was accelerating some particles and not others, in a pattern that no existing model reproduced. Somewhere, either the models were missing a physical process, or the shock itself was behaving non-uniformly, meaning it accelerated particles at different rates in different places around its surface. A non-uniform shock would mean the entire boundary of our solar system is asymmetric, not a perfect sphere, a lumpy, uneven surface that responds differently to solar activity and interstellar pressure depending on direction. That idea, considered radical when it first appeared in the data, is now accepted. The heliosphere is shaped, confirmed by later evidence, like a comet with a blunt leading edge and a long trailing tail stretched behind us as our solar system moves through the galaxy. Second surprise, the magnetic field direction at the crossing did not align with the theoretical prediction for how the solar wind's magnetic spiral should intersect the shock boundary. Field lines at the shock tilted at an angle that implied the local interstellar magnetic field, the ambient field of the galaxy pressing in from outside, was oriented differently than galactic models assumed. Think of it as two rivers meeting. You can predict the turbulence at the confluence if you know the direction and speed of both rivers. Scientists thought they knew the direction of the galactic river. The termination shock data said they had it wrong. One reading, two foundational surprises, and Voyager 1 was still millions of miles from the true outer boundary. The science team published, debated, revised, and kept watching the data stream in from a machine 35,000 miles per hour across from the only world humanity has ever called home. What came next in the data, from the region beyond the termination shock, produced a discovery so strange that scientists struggle to name it properly. A ribbon, glowing, circling the outer edge of the heliosphere. Detected not by Voyager 1 directly, but by a spacecraft specifically launched to look at what Voyager 1 had stirred everyone up about. The ribbon had no explanation. It still does not have a complete one. Beyond the termination shock, Voyager 1 entered a region with no precedent in human observation. Scientists called it the heliosheath. The word sounds clinical. The reality was anything but. Imagine the foam that forms when a river crashes into a dam. The water behind the dam does not flow clearly. It churns. It rolls back on itself. It creates turbulent eddies that move in every direction, pressing against the barrier and pushing outward simultaneously. The heliosheath is the solar system's version of that foam, a pressurized, tangled zone where solar wind, denied its outward flow by interstellar pressure, churns in relative confinement. Voyager 1 entered this zone in December 2004 and did not exit it until August 2012, 7 years and 8 months inside the foam. The models had suggested a much thinner crossing. Some estimates put the heliosheath at a few billion miles thick. The actual measurement, taken by the only instrument ever to cross it, was closer to 3 to 4 billion miles depending on the direction. That discrepancy mattered enormously. A thicker heliosheath means a different pressure balance between our solar system and the surrounding interstellar medium. It means the two environments are interacting with different strengths than theorized. And the conditions inside were extreme by any measure. Temperatures in the heliosheath, confirmed by Voyager 1's instruments, reached several 100,000 degrees. For comparison, the surface of our star sits at roughly 10,000 degrees. The heliosheath was hotter, dramatically hotter. This seems counterintuitive. You are moving away from the energy source. Why would things get hotter? The answer lies in how the plasma behaves when compressed. When solar wind material piles up against the termination shock and slows, its kinetic energy, the energy of motion, converts into heat. The faster the particles were moving, the hotter they become when stopped. The plasma in the heliosheath has been compressed and shocked to extreme temperatures. And it stays that way because there is nowhere for the heat to dissipate efficiently in a near vacuum. The magnetic field inside the heliosheath added another layer of strangeness. Instead of the relatively organized spiral pattern of the inner solar system, Voyager 1 measured a field that folded and tangled, reversing direction multiple times as the probe moved through it. Scientists call these magnetic sector boundaries. In the inner solar system, they appear at regular intervals. In the heliosheath, they were packed densely together, compressed by the same pressure that compressed everything else. Every 6 hours, Voyager 1 sent back another batch of readings. Each batch added to a picture that no textbook had prepared anyone for. The heliosheath was dense with energetic neutral atoms, particles produced when solar wind ions steal electrons from interstellar atoms drifting in. These neutral atoms fly freely in all directions, including back toward the inner solar system, where they can be detected by instruments much closer to Earth. A spacecraft called IBEX, launched in 2008 specifically to map those neutral atoms, used them to create the first map of the heliosheath as seen from inside. What that map revealed was a structure nobody had predicted, a glowing ribbon curving across the outer boundary of the heliosphere, brighter than everything around it, running perpendicular to the direction of the local interstellar magnetic field, covering roughly a quarter of the entire sky as seen from Earth. Something at the edge of our solar system was glowing, and nobody knew what it was. 7 years is a long time to be inside a wall. When Voyager 1 crossed the termination shock in 2004, the leading models gave it between 1 and 3 years to cross the heliosheath and exit into interstellar space. 1 year if the boundary was thin and the pressure balance between our solar system and the galaxy was close to predictions. 3 years if conditions were slightly different. The science team planned around those estimates, running projections for when they expected to see the signature of a true crossing. 3 years passed, then 4, then 5. The probe kept transmitting. The heliosheath kept going. By year 6, the science team was no longer working from the original models. Those had been discarded. New models were being built from the data Voyager 1 itself was generating, a circular process with no external reference point. They were mapping an unknown territory using only one instrument and revising the map as they went. The extended crossing was significant for a reason beyond pure distance. A thicker heliosheath means the pressure from outside the solar system, from the interstellar medium, is weaker than assumed. Our star's bubble is larger and more dominant than the models suggested. The heliosphere is pushing further into the surrounding galaxy than anyone calculated. But here is the complication. That interpretation is directional. Voyager 1 left in one specific direction, angled upward out of the plane of the planets, heading toward the constellation of Fucus. The heliosheath in that direction might be thicker or thinner than in other directions. When Voyager 2 crossed the heliosheath years later, on a different trajectory, its crossing was shorter and revealed different conditions. The heliosphere is shaped asymmetrically. Confirmed, different sides have different thickness, different temperatures, different particle populations. This asymmetry changes everything about the shielding model. If the heliosphere is thicker on one side and thinner on another, then the cosmic radiation reaching our inner solar system varies depending on which part of the galactic environment our solar system is moving through at any given time. Right now, our solar system is drifting through a region of the galaxy where the interstellar pressure on the leading edge of the heliosphere is higher than on the trailing edge. The heliosphere is compressed on one side and stretched long on the other, like a comet shape. That compression affects how much shielding the inner planets receive. Over geological timescales, our solar system has moved through different regions of the galaxy with different interstellar densities. Scientists now believe that during periods when the surrounding interstellar pressure was extremely high, the heliosphere might have compressed dramatically, potentially reducing the shielding around Earth enough to allow higher cosmic ray levels at the surface. Elevated cosmic rays at the surface would affect DNA mutation rates. It could affect climate through ionization of the upper atmosphere. The connection between our solar system's galactic position and conditions on Earth's surface turns out to be real and measurable, even if the mechanisms are still being studied. The 7-year crossing revealed all of this. An extended journey through churning plasma that rewrote models, reshaped the theoretical heliosphere, and connected the boundary of our solar system to the history of life on Earth. And still, the strangest discovery from that crossing had not been fully explained. Something inside the heliosheath was organizing the particles into lanes, specific, directional lanes, like a magnetic highway system built by no known force. Late in 2012, Voyager 1's instruments detected something that did not fit any model of the heliosheath. The charged particles around the probe started behaving in an organized way, Specifically, low-energy particles from inside the solar system began flowing outward along specific directions, and high-energy cosmic rays from outside began flowing inward along the same specific directions, in the opposite sense. Two streams of particles, one from inside our solar system and one from the galaxy beyond, were sharing the same lane in the magnetic field, moving in opposite directions at the same time. Scientists called these features magnetic highways, and the name captures something real about the structure. Inside the chaotic helios sheath, where the magnetic field had spent years reversing, folding, and tangling, these highway regions were different. The field lines in these zones ran in a single, consistent direction for extended stretches. Particles followed them like trains on a track. The highways were the first hint that something was changing. Voyager 1 was approaching the true outer boundary of the heliosphere. The magnetic field was shifting from the tangled mess of the helios sheath into something with more structure, a structure imposed not by our star's magnetic influence, but by the interstellar magnetic field from outside. Here is why that structure matters. Inside the heliosphere, our star's magnetic field dominates. It spirals outward, and everything inside follows its geometry. Outside the heliosphere, the galaxy's own background magnetic field runs in a completely different direction. At the boundary, the two fields must connect. They must transition from one geometry to another. The magnetic highways were that transition happening in real time. What made the discovery strange was not the existence of a transition, which theorists had predicted broadly. It was the sharpness and organization of it. Instead of a gradual, messy blending of the two fields, Voyager 1 measured relatively clean lanes where the transition happened in a structured way. The particles did not diffuse randomly across the boundary. They organized themselves along field lines and streamed. A team analyzing the data described it at the time as finding a corridor in a maze. Inside the helios sheath, everything was tangled and directionless. Then, suddenly, a lane. A clear path with organized flow. The boundary was imposing its structure from the outside, reaching inward through the helios sheath with fingers of organized magnetic geometry. This raised an immediate question that the data alone could not answer. How far did these highways extend inward? Were they a narrow feature right at the boundary? Or did organized interstellar magnetic structure penetrate deep into the helios sheath, potentially reaching regions that affected particle flow much closer to the planets? The answer was not resolved by Voyager 1 alone, but the question it raised changed how scientists think about the connection between the interstellar environment and the inner solar system. If interstellar magnetic structure can reach inward along organized pathways, then the galaxy's influence on our solar system is more direct and more continuous than any model had assumed. And this discovery came just months before the crossing that would rewrite everything. The heliopause was close. The probe was almost out, and the moment it crossed into true interstellar space, every instrument on board would be measuring an environment that had never been sampled by anything built by humans. The data about to arrive would be unlike anything received before. In 2009, a spacecraft called IBEX mapped the outer edge of our solar system using a technique Voyager 1 could not perform. Instead of flying through the boundary, IBEX stayed in Earth's orbit and mapped the energetic neutral atoms streaming back from the helios sheath. Particles produced when solar wind ions steal electrons from interstellar atoms drifting across the boundary. The map it produced should have looked roughly uniform. Helios sheath material distributed across the sky in a pattern reflecting the overall shape of the heliosphere. Perhaps brighter where the heliosphere was compressed, dimmer where it stretched. What IBEX detected was a ribbon, a bright, narrow arc of intense particle emission curving across the sky, roughly a quarter of the entire visible sphere, brighter by a factor of 2 to 3 than everything around it. The ribbon followed no predicted contour of the heliosphere. It did not align with the termination shock. It did not follow the heliopause boundary. It sat at an angle that matched almost perfectly the orientation of the local interstellar magnetic field. Scientists had never predicted it. No model had produced it. No theory had suggested it should exist. The ribbon appeared to be located right at the outer edge of the heliosphere, in the zone where our solar system's magnetic influence and the interstellar magnetic field interact. The particles emitting from the ribbon were energetic neutral atoms, solar wind protons that had crossed into interstellar space, stolen electrons from interstellar hydrogen atoms, and then curved back toward the heliosphere, following the local interstellar magnetic field. The leading hypothesis, developed over years of analysis, is that the ribbon forms where the local interstellar magnetic field runs tangent to, meaning it just grazes the surface of, the heliosphere. In those regions, neutral atoms that escape the heliosphere get ionized by interstellar radiation, get picked up by the local interstellar magnetic field, curve around, and come back toward the heliosphere from outside, emitting a signal as they do. That process, called neutral atom recycling, would produce exactly the arc ibex detected, but reproducing the ribbon's brightness, its precise geometry, and its intensity distribution has been difficult. Every model that gets close to matching it introduces new parameters that require additional explanation. A second hypothesis suggests that the interstellar magnetic field traps some returning neutral atoms in a region just outside the heliopause, building up a concentration that glows brighter than its surroundings. The geometry of this trapping region would naturally follow the field's orientation, producing an arc. Both hypotheses are active. Neither fully explains the ribbon. And here is what makes this deeply significant. The ribbon is a feature of our solar system's interaction with the galaxy around it, detectable from Earth using the right instrument. It marks a boundary whose structure we are still working to understand. Studying it means studying how our solar system fits into its galactic neighborhood, how the interstellar magnetic field shapes our heliosphere from the outside, and how that shaping affects conditions inside. The ribbon is also dynamic. Follow-up observations show that it changes over time, brightening and dimming in response to changes in solar activity. The heliosphere breathes. The ribbon breathes with it. Voyager 1 could not image the ribbon from inside the heliosheath. It was too deep inside the structure to see the whole picture, but it was generating the raw material that created the ribbon, flying through the very region where that strange arc forms. And then it crossed out of the heliosphere entirely. What waited on the other side was denser, hotter, and more magnetic than anyone had calculated. Voyager 1 carried a plasma science instrument. Its job was to measure the density, temperature, and flow direction of plasma, the superheated, ionized gas that fills the heliosphere and the space beyond. For the inner mission near Jupiter and Saturn, it worked exactly as designed, characterizing the plasma environments around those giant planets with precision. Then, in 1980, it stopped working correctly. A failure in one of the instrument's detectors left it unable to measure the supersonic solar wind blowing outward from our star. The component that failed was specifically the part designed to catch the fast directional flow of the solar wind itself. The remaining components could still measure lower energy plasma, but the ability to directly sample the main solar wind stream was gone. For a mission focused on the outer heliosphere and interstellar boundary crossing, this was a serious loss. Scientists adapted. They used other instruments to infer some of what the plasma instrument would have measured directly. The low-energy charged particle detector could track particle energies and flux. The magnetic field instrument provided the field geometry. The plasma wave instrument could detect the frequency of oscillations in the surrounding plasma, which relates to plasma density through a well-known physical relationship. Together, these indirect measurements gave a partial picture of the plasma environment around the probe. But partial is the key word. When Voyager 1 crossed the termination shock in 2004, and then spent years moving through the heliosheath, scientists could not directly measure the plasma density and flow with the precision the original instrument would have provided. Entire categories of data that would have settled scientific debates in months instead required years of indirect analysis. Here is the strange part. The instrument's silence became its own kind of data. When the plasma wave instrument detected oscillations in 2012 and 2013, shortly after the heliopause crossing, scientists could use the frequency of those oscillations to calculate the density of the surrounding plasma. Plasma oscillates at a frequency that depends directly on how many charged particles per cubic meter are present. The denser the plasma, the higher the frequency. The plasma wave readings after the heliopause crossing showed oscillation frequencies significantly higher than those inside the heliosphere. The plasma outside was denser, how much denser became the subject of precise calculation from those wave frequencies, and the answer was approximately 40 times denser than the plasma inside the heliosheath. 40 times. The interstellar medium was far more concentrated than the theoretical models had predicted. This single measurement, derived not from the plasma instrument itself, but from the plasma wave instrument detecting a ripple in the medium, forced an immediate revision of interstellar medium density models. The galaxy's ambient plasma, at least in the region immediately beyond our heliosphere, was more substantial than assumed. What this means for the heliosphere itself is significant. A denser interstellar medium pressing inward means the pressure balance that determines the heliosphere's size is different from calculations. A denser external medium compresses the heliosphere more strongly. The balance point shifts inward. Our protective bubble may be somewhat smaller than we calculated in those theoretical models, and the failed instrument kept teaching. Every anomaly, every silence, every indirect measurement added another layer to a picture that the original mission designers never imagined they were building. But all of that analysis depended on one confirmed fact: knowing exactly when Voyager 1 had truly crossed into interstellar space. That moment was controversial. The argument over it ran for years. August 25th, 2012. That is the date scientists eventually agreed upon for the most significant boundary crossing in the history of spaceflight. After 35 years of travel, Voyager 1 crossed the heliopause and entered interstellar space. The heliopause is the true outer boundary of the heliosphere. Beyond the termination shock and the churning heliosheath, the heliopause is the line where our star's influence effectively ends. Inside it, the solar wind, however slowed and compressed, still dominates the particle environment. Outside it, the interstellar medium takes over completely. Solar wind particles stop. Galactic particles flood in. The magnetic field switches from our star's geometry to the galaxy's geometry. The crossing was confirmed in 2 steps because determining whether you have truly left the heliosphere is harder than it sounds. First, in the weeks around August 25th, Voyager 1's instruments recorded a sharp, sustained drop in low-energy particles from inside the solar system, combined with a sharp, sustained rise in galactic cosmic rays from outside. The transition happened fast. Within days, the particle environment flipped from heliospheric to interstellar. That was the first strong signal. But scientists needed more. A particle shift alone could potentially reflect a transient feature inside the heliosheath, a local boundary rather than the true heliopause. What they needed was a magnetic field confirmation. The magnetic field data provided it, but with a complication. At the heliopause, the expected signature was a change in magnetic field direction, from the spiral geometry of our star's field to the orientation of the interstellar galactic field. Voyager 1's magnetometer did show a change. The field direction shifted, but the magnitude of the shift surprised the team. The interstellar magnetic field just outside the heliopause ran in a direction broadly similar to our star's field in that region, closer in angle than most models had predicted. It was not the sharp 90-degree flip some theoretical models expected. It was a more gradual angular change that fit with a specific model of how the 2 fields align at the boundary. This alignment, confirmed by the Voyager 1 data, suggested that the local interstellar magnetic field is oriented in a way that shapes our heliosphere significantly, compressing it from one side and stretching it in another. The heliosphere's comet-like shape traces partly to this external magnetic pressure. What made August 25th definitive was the plasma wave instrument reading from October 2012. A large eruption from our star sent a pressure wave outward through the heliosphere. That wave reached Voyager 1's location months later, in April 2013. When it hit the surrounding plasma, it caused oscillations that the plasma wave instrument detected. The frequency of those oscillations corresponded to a plasma density 40 times higher than inside the heliosphere. 40 times. Clean, unambiguous confirmation that the probe was in a completely different medium. Voyager 1 had crossed out completely. For the first time in human history, a machine built by people on Earth was operating in the space between stars. The instruments were still running, the data was still coming, and every reading from this new environment was a first. No model had ever been validated against actual interstellar medium data before. The first readings were already rewriting models, and what they found about the true nature of interstellar space was far stranger than a quiet, cold emptiness. Before Voyager 1 sent back readings from beyond the heliopause, the interstellar medium had a reputation: cold, thin, empty. The textbook version of the space between stars was a near vacuum, a few atoms per cubic yard, temperatures close to absolute zero, magnetic fields so weak they barely registered. The data from Voyager 1's first confirmed measurements in interstellar space revised every one of those assumptions. The plasma density, as measured by the plasma wave oscillation frequency, was roughly 40 times higher than models predicted for that region. 40 times. The interstellar medium just beyond our heliosphere is not a gentle void. It is a crowded, pressurized environment by the standards of space plasma physics. The atoms and ions present are sparse compared to anything on Earth, but they are far more numerous than theoretical models of that specific galactic neighborhood suggested. The temperature of the plasma was also surprising. Models expected the interstellar medium immediately beyond the heliopause to be cold, perhaps a few thousand degrees in the plasma temperature sense. Instruments indicated a temperature much higher than that baseline, reflecting the dynamic nature of the region just outside the boundary. The heliopause is an active interface, not a quiet wall. Energy flows across it, particles exchange between the two environments, and that exchange heats the boundary region on both sides. The magnetic field was the third surprise. Just outside the heliopause, Voyager 1 measured a field stronger than predicted and oriented at an angle that did not match the dominant models of the local interstellar magnetic environment. Galactic magnetic field maps, built from decades of observations of distant pulsars and radio emission from the Milky Way, pointed to a field direction that the Voyager data partially contradicted. Specifically, the local interstellar magnetic field in our immediate galactic neighborhood appears to be tilted relative to what the large-scale galactic models suggest. This implies that our solar system sits in a region where the local magnetic environment is influenced by nearby structures, possibly old supernova remnants, or the magnetic imprints of massive stars that died millions of years ago in our galactic neighborhood. Here is what that means in practical terms. The interstellar space our heliosphere is currently embedded in carries the magnetic signature of ancient violence. Stars exploded, their remnants pushed and twisted the local magnetic field, and our solar system is drifting through a region still shaped by those long-ago events. The local interstellar cloud, the diffuse gas cloud our solar system is currently traveling through, has a magnetic field shaped partly by this history. And that field, pressing on our heliosphere from the outside, is what gives the heliosphere its asymmetric, comet-like shape. Voyager 1 was measuring, for the first time, the environment that has been shaping our solar system's protective boundary for millions of years. The measurements were real, confirmed, and increasingly detailed as the probe moved deeper into interstellar space. But the deeper Voyager 1 moved, the more a different question grew in urgency. Our solar system is moving through the galaxy, through the local interstellar cloud, and eventually toward the edge of that cloud. Scientists estimate our solar system will reach the boundary of the local interstellar cloud in somewhere between a few thousand and tens of thousands of years. What lies beyond that cloud is raw interstellar space with very different properties. And what those properties would do to the heliosphere and to the planets inside it is a question that Voyager 1's data is only beginning to help us answer. The number arrived quietly, a frequency reading from the plasma wave instrument transmitted across 14 billion miles, decoded by scientists at the Jet Propulsion Laboratory, and converted into a single measurement of plasma density. The result stopped the room. The interstellar medium just beyond the heliopause was roughly 40 times denser than the leading theoretical models had predicted for that location. 40 times. In science, a factor of 2 is significant. A factor of 10 demands explanation. 40 demanded a complete reassessment of the models used to describe our galactic neighborhood. To understand why this matters, picture the heliosphere as a balloon being blown up inside a room. The size of the balloon depends on two things: the pressure of the air being pumped in, and the pressure of the air in the room pushing back. If the room's air pressure is higher than you thought, the balloon will be smaller than you calculated. The heliosphere works exactly this way. Our star pumps solar wind outward. The interstellar medium pushes inward. The balance point determines where the heliopause sits. If the interstellar medium is 40 times denser than assumed, the inward pressure is significantly higher than the models calculated. That means the heliosphere should be smaller, more compressed than every pre-Voyager model indicated. Our protective bubble might be substantially tighter around our solar system than we believed, and this has a direct consequence for life on Earth. The heliosphere's primary function, from a biological perspective, is shielding. It deflects and absorbs a significant fraction of galactic cosmic rays before they reach the inner planets. A smaller, more compressed heliosphere means less shielding distance. More cosmic rays penetrate deeper before being absorbed. Some fraction of those additional cosmic rays reaches Earth's upper atmosphere, ionizes molecules there, and potentially affects cloud formation, chemistry, and radiation exposure at the surface. Scientists emphasize that the current heliosphere provides substantial shielding, even accounting for the revised density figures. Life on Earth is not in immediate danger from this recalculation. But over geological timescales, when our solar system moves through regions of even higher interstellar density, the compression could be more extreme. The plasma density reading also revealed something about the structure of the local interstellar cloud itself. The cloud our solar system is currently drifting through is not uniform. Different regions have different densities. Our position within the cloud, in a region denser than average for this type of structure, partly explains the elevated reading Voyager 1 detected. Scientists built new models incorporating the measured density. Those models produced a heliosphere smaller and more dynamically responsive to interstellar conditions than previous versions. The revised heliosphere breathes more rapidly in response to solar activity changes. Its boundary moves more aggressively in response to interstellar pressure variations. The balloon is more responsive than anyone thought, and the room it sits in is more crowded. But the plasma density was just the first number that broke the model. The magnetic field direction, waiting just outside the heliopause, carried a second, equally fundamental surprise. One that reached back not just to our star, but to the violent history of the entire galactic neighborhood our solar system calls home. Something ancient had left its fingerprint on the space surrounding us, and Voyager 1 had just measured it. A magnetic field has two properties that matter most: its strength and its direction. Voyager 1's magnetometer measured both continuously throughout the entire journey from Earth to interstellar space. The readings from inside the heliosphere confirmed existing models reasonably well. The solar wind carries a magnetic field that spirals outward from our star, bending as it travels, following a geometry first described mathematically in the 1950s. But the moment Voyager 1 crossed the heliopause, the field changed. The direction shifted. The field outside the heliosphere ran at an angle that the prevailing models of the local interstellar magnetic environment did not predict. Galactic magnetic field maps, assembled over decades from observations of distant radio sources and pulsars scattered across the Milky Way, pointed to a specific orientation for the field in our galactic neighborhood. The Voyager 1 data matched that large-scale orientation only partially. Locally, right outside our heliosphere, the field was tilted. The tilt was not massive, but in magnetic field geometry, even a modest angular offset carries significant information. It tells you that the local environment has been disturbed. Something has twisted the field away from its background galactic orientation in this specific region of space. The leading explanation connects to the history of our galactic neighborhood, a region astronomers call the local bubble. Roughly 14 million years ago, a series of massive stars in our galactic region burned through their fuel and exploded as supernovas. Each explosion released energy equivalent to roughly 10 to the power of 44 joules, numbers that resist intuitive grasp, but whose effects are still visible today. Those explosions carved out a vast, hot, low-density cavity in the interstellar medium. Our solar system currently sits inside this cavity, which spans roughly 1,000 light-years across. The supernovas that created the local bubble also magnetized and oriented the gas at its boundary. The local interstellar cloud, The smaller, denser clump of gas our solar system is currently drifting through, within the larger cavity, sits near the edge of the local bubble. Its magnetic field carries the imprint of those ancient stellar deaths. The orientation Voyager 1 measured just outside our heliosphere reflects, in part, the magnetic legacy of stars that exploded millions of years before complex life appeared on Earth. Voyager 1 did not just measure our current environment, it measured history. The angular offset between the large-scale galactic field and the local field measured by Voyager 1 remains a subject of active research. Matching the two requires detailed modeling of how supernova remnants magnetize and structure the interstellar medium over millions of years. Several research groups have published competing models. None perfectly reproduces the measured offset. What the data confirmed, beyond debate, is that the interstellar space immediately surrounding our heliosphere is magnetically complex, shaped by multiple influences, not describable by simple large-scale models alone. This complexity matters for the heliosphere's shape, for the ribbon of energetic neutral atoms that IBEX detected, and for the long-term stability of our solar system's shielding properties as it moves through different parts of the local bubble over millions of years. The magnetic field direction mystery also reinforced a broader truth the Voyager data kept delivering. The environment our solar system exists in has been shaped by events far older and more violent than our star itself. We are drifting through the archaeological site of an ancient catastrophe, and the cosmic rays flooding through that environment carry the most direct evidence of how violent the galaxy truly is. The moment Voyager 1 crossed the heliopause, one instrument reading spiked immediately, and, dramatically, the galactic cosmic ray count jumped. Within days of crossing the boundary, the probe's cosmic ray detector registered a flood of high-energy particles streaming in from every direction. Particles that had been largely blocked or deflected by the heliosphere were suddenly present at full interstellar intensity. Galactic cosmic rays are particles, mostly protons but also heavier atomic nuclei, accelerated to extraordinary speeds by the most violent events in the universe. Supernovas are the primary factory. When a massive star collapses and explodes, the shockwave it produces accelerates surrounding particles to speeds approaching the speed of light. Those particles travel outward in all directions, crossing the galaxy for millions of years, filling the interstellar medium with a constant rain of high-energy projectiles. By the time they reach our solar system, they carry energies millions of times higher than anything a particle accelerator on Earth currently produces. A single galactic cosmic ray proton can carry the kinetic energy of a baseball, thrown at a moderate pitch, compressed into a single subatomic particle, traveling at nearly the speed of light. Inside the heliosphere, the solar wind and its magnetic field deflect and slow a substantial fraction of these particles. Lower energy cosmic rays get scattered and absorbed before reaching the inner planets. Higher energy ones punch through, but at reduced intensity. The heliosphere provides what scientists describe as a rigidity cutoff, meaning particles below a certain energy level cannot penetrate to the inner solar system regardless of their direction. Outside the heliosphere, that cutoff disappears. Voyager 1's instruments measured galactic cosmic rays at their full interstellar intensity for the first time. The reading confirmed something planetary scientists had suspected but never directly verified. The heliosphere reduces the cosmic ray flux at Earth by a factor that varies with solar activity but averages somewhere between roughly 50 and 75% for lower energy particles. Remove the heliosphere, and the radiation environment at Earth's surface would change substantially. Over Earth's history, there have been periods when galactic cosmic ray flux at the surface was elevated. Scientists find evidence of these periods in cores drilled from Antarctic ice, in chemical signatures in deep-sea sediments, and in the record of isotopes produced by cosmic ray bombardment of atmospheric molecules. The correlation between elevated cosmic ray periods and geological events remains an active area of study. What Voyager 1 added to this story was the first direct measurement of what the cosmic ray environment looks like, without heliospheric shielding. Every number the probe recorded outside the heliopause represents the baseline bombardment our solar system's bubble has been protecting us from, continuously since before complex life evolved. The cosmic ray data also helped confirm the moment of Voyager 1's heliopause, crossing more precisely than any other measurement. The jump in cosmic ray intensity was sharp, clean, and sustained. It did not fluctuate back and forth the way the termination shot crossing had. Once the probe crossed into interstellar space, the cosmic ray count stayed elevated. The heliosphere was behind it, fully and permanently. But something about the cosmic ray data raised a deeper puzzle. The rays were arriving from all directions, equally completely isotropic in scientific terms, suggesting no dominant nearby source was overwhelming the background. If there were a nearby supernova remnant actively accelerating cosmic rays in our galactic neighborhood, the distribution would be uneven. The isotropy suggested our current position in the local bubble is relatively quiet, cosmically speaking. Relatively quiet, however, does not mean static. And the next discovery from Voyager 1's data would challenge what scientists thought they knew about the very shape of the structure protecting us from all of it. For decades, the model was clean and confident. Our solar system moves through the interstellar medium at roughly 53,000 miles per hour relative to the surrounding gas. At that speed, models predicted our heliosphere would push through the interstellar medium like a ship through water, creating a shockwave in front of it. A bow shock, a compressed region of heated interstellar gas, piling up ahead of the heliosphere's leading edge, exactly like the wave that forms in front of a boat's hull. This feature appeared in textbook diagrams. It appeared in scientific papers stretching back decades. It was a standard component of heliospheric models, taught in university courses, depicted in NASA animations. Then, the data arrived and erased it. The first serious challenge came from observations made by IBEX in the early 2000s. Maps of energetic neutral atoms streaming back from the outer heliosphere did not show the signature a bow shock would produce. The heating and compression expected ahead of the leading edge of the heliosphere were absent. Something was different from the prediction. The explanation, which emerged from combining the IBEX data with Voyager 1's magnetic field measurements, came down to a single factor. The interstellar magnetic field is stronger than the models assumed. A bow shock forms when an object moves faster through a medium than the fastest wave that medium can carry. In a fluid like water, that fastest wave is the speed of sound. In magnetized plasma, the relevant speed is higher because magnetic fields transmit waves of their own, called alphen waves, which add to the effective wave speed of the medium. If the interstellar magnetic field is strong enough, the alphen wave speed in the surrounding plasma exceeds our heliosphere's velocity through it. In that case, no shockwave forms ahead of the heliosphere. The medium can get out of the way fast enough. The bow shock disappears. Voyager 1's measurement of interstellar magnetic field strength, combined with the elevated plasma density reading, produced exactly this result when plugged into the wave speed equation. The heliosphere is moving through the interstellar medium subsonically. In the magnetic sense, no bow shock exists. A broader, gentler compression region forms ahead of the heliosphere instead, called a bow wave, but the classic shock wave is absent. This was not a minor correction. The bow shock had been in the standard model for so long that removing it required confronting how much of that model had been built on assumed rather than measured values. The interstellar magnetic field strength, which controls whether a bow shock can form, had never been directly measured before Voyager 1. One measurement from one probe eliminated a feature that had lived in the standard model for half a century. Voyager 2's crossing confirmed this conclusion from a different direction and a different angle, adding a second data point that made the conclusion impossible to dismiss. Two probes, two trajectories, same result. The bow shock is gone. What replaced it in the updated models was a more nuanced picture of how our heliosphere interacts with its galactic surroundings. A picture with a blunt, compressed leading edge, a long trailing tail stretched behind our direction of travel, and no shockwave clearing the way ahead. The shape of the entire structure was different from what we thought. And then, Voyager 2 crossed the heliopause and confirmed something even more unexpected. On November 5th, 2018, Voyager 2 crossed the heliopause. 6 years after Voyager 1, in a completely different direction, moving at a shallower angle relative to the plane of the planets, heading roughly toward the constellation Telescopium. The second probe gave scientists something extraordinarily valuable, a second data point for the most important boundary in our solar system. 2 crossings, 2 directions, 2 independent measurements of the conditions at the heliopause. The confirmed results were significant. Both probes detected the same sharp jump in galactic cosmic rays at the crossing. Both measured a shift in magnetic field direction from heliospheric to interstellar geometry. Both found the plasma density outside the heliopause substantially higher than pre-mission models predicted. The broad picture that Voyager 1 had delivered held up under independent verification. But the differences between the 2 crossings were scientifically just as valuable as the similarities. Voyager 2 crossed the heliopause at a distance from our star of roughly 11 billion miles. Voyager 1 had crossed at approximately 14 billion miles. The heliopause in Voyager 2's direction is significantly closer to our star than in Voyager 1's direction. The heliosphere is not a sphere. It is compressed on one side and extended on the other. This asymmetry confirmed the comet tail model of the heliosphere directly, with real boundary measurements rather than theoretical inference. The compressed side faces roughly into the direction the solar system is moving through the interstellar medium. The extended side trails behind. The difference in heliopause distance between the 2 probes, roughly 3 billion miles, quantifies that asymmetry for the first time. Voyager 2 also carried a functional plasma science instrument, the same type that had failed on Voyager 1 in 1980. For the first time, direct plasma measurements at the heliopause crossing were available. The plasma data confirmed the density increase independently and provided temperature measurements that the indirect method on Voyager 1 could only approximate. Those temperature readings produced an immediate puzzle. At the heliopause, the solar wind plasma trapped inside the heliosheath should cool as it approaches the outer boundary. Models predicted that the plasma temperature at the heliopause interior would be relatively low. Voyager 2's plasma instrument found a temperature approximately 10 times higher than expected at the inner edge of the heliopause crossing. 10 times hotter. The plasma was not cooling as it approached the boundary. Something was heating it from outside, or energy was somehow flowing inward through the heliopause rather than being blocked by it. Scientists proposed that the heliopause is leakier than models assumed. Interstellar particles, specifically energetic neutral atoms from outside, can cross the heliopause and deposit energy into the heliosheath plasma near the boundary. This leakage heats the boundary layer from outside. The magnitude of the heating Voyager 2 measured helped quantify how permeable the heliopause actually is. And the answer was more permeable than any previous model had considered. The boundary between our solar system and interstellar space is not a wall, it is a membrane. It leaks in both directions, and the leakage carries energy, particles, and influence between 2 very different environments in ways that are still being worked out. The shape of what comes next, what the heliosphere looks like from the outside, and what our solar system is actually drifting through, followed directly from combining both probes' datasets. The picture that emerged was stranger and more beautiful than any diagram in any textbook. Both Voyager probes agreed on something fundamental. The heliosphere's boundary region runs far hotter than the cold void surrounding it. This agreement across 2 probes, 2 directions, and 2 different instrument configurations made the result impossible to dismiss as measurement error. The temperature paradox sits at the intersection of 2 competing forces. Moving away from a heat source, you expect things to cool. The outer heliosphere is billions of miles from our star. The solar wind, by the time it reaches the termination shock, has cooled considerably from its original several million degree temperature near our star's corona. Standard adiabatic cooling models, which describe how a gas cools as it expands, predict the plasma at the outer heliosphere should be relatively cool, hundreds of thousands of degrees at most. Instead, both probes measured plasma temperatures in the heliosheath far exceeding those prediction, and immediately inside the heliopause, where Voyager 2's plasma instrument took its most precise readings, the temperature was higher still. Scientists identified several processes contributing to this excess heat, and the combination reveals how actively the heliospheric boundary processes energy. First, the termination shock itself heats the plasma it processes. When supersonic solar wind slams into the shock boundary and slows dramatically, kinetic energy converts to thermal energy. The efficiency of this conversion, how much of the wind's motion becomes heat, is higher than the original models assumed because the shock is not a simple smooth boundary. It is turbulent. The turbulence increases the heating rate. Second, inside the heliosheath, magnetic reconnection events continuously release energy. Magnetic reconnection happens when two magnetic field lines pointing in opposite directions are forced together. They break, reconnect in a new configuration, and release energy directly into the surrounding plasma as heat and particle acceleration. The heliosheath's tangled, compressed magnetic field is an ideal environment for continuous reconnection. Every reconnection event adds heat to the plasma trapped in the sheath. Third, energetic neutral atoms streaming in from interstellar space deposit energy inside the heliosheath as they ionize and become part of the plasma population there. This inward energy flux from outside the heliopause heats the inner boundary layer continuously. These three mechanisms together push the temperature at the heliopause interior above what any single process model predicted. The heliosheath is a thermodynamic engine, constantly processing energy from multiple sources simultaneously. The temperature paradox also revealed something important about how we use spacecraft data to infer conditions we cannot measure directly. Before Voyager 2's plasma instrument confirmed the high temperatures with direct measurement, the indirect estimates from Voyager 1 suggested elevated temperatures but could not precisely quantify them. The direct confirmation from Voyager 2 validated the indirect analysis method, which is now used to interpret other aspects of Voyager 1's data with greater confidence. But the temperature readings carry an implication that reaches beyond heliospheric physics. A hotter, more energetically active boundary region means the heliopause is a site of constant energy exchange between our solar system and the galaxy. Our heliosphere does not passively float in interstellar space. It interacts with it dynamically. Energy flows in and out continuously. Particles cross in both directions. The two environments are coupled. Understanding that coupling is important for modeling what happens when our solar system moves into a different region of interstellar space, with different density and temperature properties. The heliosphere's response to those changes will play out through exactly the mechanisms revealed by the temperature paradox data. And the shape of the heliosphere, confirmed by combining both probe crossings with the temperature data, has now been mapped with enough precision to tell a far larger story. For most of the 20th century, diagrams of the heliosphere showed a sphere, slightly compressed on one side perhaps, but essentially round, a bubble centered on our star, expanding evenly in all directions until solar wind pressure equaled interstellar pressure. Voyager 1 and Voyager 2 together destroyed that picture permanently. The heliopause in Voyager 1's direction sits roughly 14 billion miles from our star. In Voyager 2's direction, it sits roughly 11 billion miles. A 3 billion mile difference in boundary position, depending on which direction you measure. That difference is too large to dismiss as local variation. It reflects a fundamental asymmetry in the heliosphere's shape. The modern picture, assembled from both crossings combined with ibex neutral atom maps and computer simulations constrained by real measurements, shows a heliosphere shaped broadly like a comet, a blunt, rounded leading face, pointing into the direction of travel through the interstellar medium, a long stretched tail trailing behind. Our solar system moves through the galaxy at roughly 53,000 miles per hour relative to the surrounding interstellar gas. As it moves, the interstellar medium presses harder on the leading edge of the heliosphere, compressing it. The solar wind on the trailing side faces less resistance and expands further before losing the battle against interstellar pressure. The tail, called the heliotail, extends for distances that are difficult to directly measure. Based on neutral atom maps from IBEX and computer models calibrated against the Voyager crossing data, the heliotail may extend several times further than the leading edge boundary distance, possibly hundreds of billions of miles. The full heliosphere, from its compressed nose to the tip of its tail, may span a region that dwarfs the distance from our star to its nearest planetary neighbors by a factor of many hundreds. But the shape is not static. It breathes. Solar activity rises and falls over roughly 11-year cycles. During solar maximum, our star is more active, erupting more frequently, sending stronger and denser solar wind outward. The increased wind pressure pushes the heliosphere's boundaries outward. During solar minimum, the reduced wind pressure allows the heliosphere to contract slightly as interstellar pressure gains ground. Both Voyager probes, operating during different phases of the solar activity cycle, detected the effects of this breathing. The heliopore's boundary shifted measurably in response to pressure waves driven by major solar eruptions. Voyager 1 detected a pressure pulse from a large eruption arriving at the heliopore's region months after the event, compressing and brightening the boundary layer temporarily. The heliosphere is alive in a dynamic sense. It responds to both internal activity and external interstellar conditions simultaneously. Its shape at any moment is the current result of a continuous negotiation between two vast systems of plasma and magnetic field. This negotiation has been ongoing for the entire 4.5 billion year history of our solar system. As our solar system has moved through different galactic environments, the negotiation has shifted. During periods inside dense interstellar clouds, the heliosphere compressed dramatically. During periods inside the hot, low-density local bubble cavity we currently occupy, it expanded to its largest extent. We are currently in the expanded phase, inside the local bubble, with a large and relatively effective heliosphere. That will eventually change, and the change, when it comes, will be driven by where our solar system is heading next. Our solar system is not drifting through empty space. Right now, every planet, every moon, every asteroid, the entire heliosphere and everything inside it is moving through a structure called the local interstellar cloud, a diffuse warm bubble of partially ionized gas, roughly 30 light-years across, embedded within the larger local bubble cavity created by ancient supernovas. The local interstellar cloud is thin by earthly standards. Its density, even denser than average interstellar space, amounts to roughly a fraction of an atom per cubic inch, a near-perfect vacuum by any laboratory measure. But extended across 30 light-years of space, even that thinness accumulates into a structure with genuine physical properties. It has a temperature, a magnetic field, a chemical composition, and a boundary. And our solar system is currently inside it, moving through it at roughly 53,000 miles per hour. Scientists identified the local interstellar cloud through observations of how it absorbs specific wavelengths of ultraviolet light from distant stars. The gas in the cloud imprints a characteristic absorption signature on starlight passing through it, and by mapping which stars show the signature and which do not, researchers traced the cloud's outline. Our solar system sits near one edge of the cloud, which means we entered it relatively recently in astronomical terms, perhaps a few tens of thousands of years ago. The Voyager data added direct measurements of the cloud's properties from inside it: the plasma density reading, the magnetic field orientation, and the temperature of the interstellar medium just outside the heliopause, all reflect conditions inside the local interstellar cloud specifically, not some average interstellar condition. What those measurements revealed is that the local interstellar cloud is slightly warmer and denser than models predicted, and that its magnetic field carries the angular offset from large-scale galactic orientation that traces back to the ancient supernovas that formed the local bubble. Our immediate galactic neighborhood carries the physical memory of stellar deaths millions of years old. The cloud is also moving. Relative to the average motion of nearby stars, the local interstellar cloud flows at roughly 59,000 miles per hour. Our solar system moves at a slightly different velocity. The combination produces the apparent wind of interstellar material that the heliosphere faces on its leading edge, compressing it into the comet shape confirmed by the Voyager crossings. Scientists now believe the cloud shields our solar system, somewhat counterintuitively, from even more extreme interstellar conditions. The local bubble surrounding the cloud is filled with extremely hot, thin plasma, the remnant gas from the supernova explosions that carved it out. That gas, far hotter than the local interstellar cloud itself, would press on the heliosphere far more aggressively if the cloud were not there to partially cushion the boundary. Inside the cloud, our heliosphere is large and relatively stable. Outside the cloud, in the raw local bubble plasma, conditions would be different, and our solar system is approaching the cloud's edge. Scientists estimate we will reach that edge in somewhere between a few thousand and a few tens of thousands of years. On a human timescale, that is an enormous span. On a geological or evolutionary timescale, it is a moment away. What waits on the other side is not a mystery. It is something measurable, predictable, and genuinely consequential for every living thing on this planet. The local interstellar cloud does something that most people never think about. It stands between Earth and conditions in the surrounding local bubble that would significantly alter our heliosphere's protective capacity. The local bubble is filled with hot, low-density plasma left behind by the supernovas that carved it. This plasma has a temperature of roughly 1 million degrees, far hotter than the local interstellar cloud material. Hot plasma carries pressure. That pressure, if it acted directly on the heliosphere without the cloud's intervention, would compress our heliospheric bubble more aggressively than current conditions do. A more compressed heliosphere means a smaller shielding volume. The termination shock would sit closer to our star. The heliosheath would be thinner. The heliopause would be closer to the inner planets. And the cosmic ray flux penetrating to Earth's surface would be higher. How much higher is a question scientists are actively modeling. The answer depends on detailed assumptions about the pressure difference between the local interstellar cloud and the surrounding local bubble plasma, and about how the heliosphere's shielding efficiency scales with size. Current models suggest that if the heliosphere were compressed to the size it would reach in raw local bubble plasma, the galactic cosmic ray flux at Earth's surface could increase by a significant factor, possibly enough to meaningfully affect atmospheric chemistry and surface radiation levels. This has happened before in Earth's history. Our solar system has crossed regions of the galaxy with higher interstellar density, compressing the heliosphere and exposing Earth to elevated cosmic ray levels. Scientists find evidence of these episodes in geological records. Enhanced production of cosmogenic isotopes, atoms created when cosmic rays strike atmospheric molecules, appears in sediment layers and ice cores at specific periods in Earth's past. Whether those elevated cosmic ray periods correlate with biological changes on Earth's surface is a subject of genuine scientific research, not settled consensus. Some studies find correlations between cosmogenic isotope spikes and periods of elevated mutation rates or climate shifts. Others find the correlations ambiguous or explainable by other factors. The debate is active and honest. What is settled is that the local interstellar cloud is providing a real physical buffer right now. The Voyager data quantified the cloud's properties directly, and those measurements feed directly into calculations of how much pressure the cloud takes off the heliosphere compared to raw local bubble conditions. We are, in a measurable sense, in a favorable location. The cloud is a haven, and our solar system is drifting toward its exit. The exit is not a cliff. It is a gradual transition, likely spanning thousands of years, during which the heliosphere will respond dynamically to changing external pressure. The heliosphere will compress. The shielding configuration will shift. Cosmic ray levels at Earth will adjust over timescales longer than human civilization. Understanding this transition is one of the most pressing reasons to continue studying the interstellar medium with every available tool. Voyager 1 gave us the first direct measurements of the environment our heliosphere sits in. Future missions, better equipped, will map the transition zone ahead of us, but the consequences of what waits beyond the cloud reach further than most people realize. Far further. Because when the heliosphere truly changes, it changes everything inside it. Stand at the edge of the local interstellar cloud and look outward into the local bubble. The plasma there is 1 million degrees. The density is far lower than inside the cloud. The pressure balance it would impose on our heliosphere is different enough to produce a qualitatively different solar system environment. A heliosphere compressed by local bubble plasma would be smaller, possibly by a factor that brings the heliopause significantly closer to the inner planets. The exact reduction depends on the pressure ratio between current conditions and local bubble conditions. Models using Voyager calibrated interstellar medium properties suggest the heliopause could sit as close as perhaps half its current distance in some scenarios. Half the distance means half the shielding path length for incoming cosmic rays. Lower energy cosmic rays that currently get absorbed within the heliosphere before reaching the inner solar system would penetrate further. The inner planets, including Earth, would experience a meaningfully elevated particle bombardment. Elevated cosmic ray flux at Earth's surface affects several systems simultaneously. At the atmospheric level, cosmic rays ionize molecules in the upper atmosphere. That ionization affects chemical reaction rates in the stratosphere and potentially influences cloud nucleation processes in the lower atmosphere. The exact magnitude of cosmic ray effects on Earth's climate remains debated among atmospheric scientists, but the physical mechanism for interaction is established and real. At the biological level, cosmic rays reaching the surface produce secondary particle showers when they strike the atmosphere. Those secondary particles, particularly muons, penetrate to ground level and contribute a small but real dose of radiation to surface life. An elevated primary cosmic ray flux increases the secondary particle production rate. Over geological timescales, sustained elevated surface radiation levels affect mutation rates in living organisms. The effect is subtle over any human timeframe. Over millions of years, it could influence the pace and direction of biological evolution. Earth has experienced dramatically different heliospheric conditions before. Our solar system has passed through dense molecular clouds that compress the heliosphere to a fraction of its current size, potentially leaving Earth with essentially no heliospheric shielding at all during those crossings. Life on Earth survived those episodes, which tells us that surface life is more robust to cosmic ray exposure than simple models suggest. But survival is a flaw, not a ceiling. The specific conditions inside the heliosphere matter for the specific type of life Earth supports at any given moment. There is also a longer-term consequence related to the interstellar neutral atoms that would flood deeper into the solar system under reduced heliospheric shielding. Some of those neutral atoms, particularly hydrogen and helium from the interstellar medium, interact chemically with the upper atmospheres of planets. The rate of those interactions depends on how many neutral atoms reach the inner solar system. A compressed heliosphere allows far more of them through. Venus, Earth, and Mars all have histories shaped partly by their interaction with the space environment around them. Earth's magnetic field and thick atmosphere provide additional shielding beyond the heliosphere. Mars lost much of its atmosphere billions of years ago, partly because it lacked that magnetic protection. Under a severely compressed heliosphere, the erosion rate of planetary atmospheres by interstellar material and elevated radiation would increase. The Voyager data made all of these calculations more accurate by replacing assumed interstellar medium properties with measured ones. The models are better now. The predictions are more grounded, and the timing of our approach to the cloud's edge is close enough, in astronomical terms, to deserve serious scientific attention. Right now, as you listen to this, a signal is crossing space. It left a spacecraft roughly 14 billion miles from Earth and began traveling at the speed of light. Even at that speed, the journey takes over 21 hours. When it arrives, it will be received by one of the massive dish antennas of NASA's Deep Space Network. Facilities in California, Spain, and Australia positioned around Earth so that one is always facing in the right direction as the planet rotates. The signal itself carries a tiny amount of power, far less than a single flashlight battery produces. Scientists describe it as arriving at Earth with less energy than a snowflake landing on the ground. And yet those 70-foot dish antennas, pointed with extraordinary precision, can catch it, amplify it, and read the data encoded within it. What that data contains is science collected by instruments that have been running for nearly 50 years on a machine the size of a small car, powered by nuclear generators that produce barely enough electricity to run a few household light bulbs. The nuclear generators on Voyager 1 use a substance called plutonium-238. As the plutonium undergoes radioactive decay, it releases heat. Thermocouples convert that heat directly into electricity through a process that requires no moving parts and no fuel combustion. The same process has been running since 1977, silently and continuously, shrinking in output each year as the plutonium decays. Each year, the generators produce roughly 4 watts less than the year before. The science team has responded by carefully managing power allocation, turning off heaters, then non-essential systems, then instruments one by one, stretching the mission's productive life as long as the physics of radioactive decay allows. Currently, Voyager 1 operates with enough power to run only a subset of its original instruments. Some heaters are off, leaving parts of the spacecraft at temperatures far below what engineers originally specified. The probe survives this because its designers built it for a harsh radiation environment near Jupiter and Saturn, which required robust construction and redundant systems that decades later continue to protect the core functions. The Deep Space Network antennas that catch Voyager 1's signal are themselves technological achievements separate from the spacecraft. Receiving a signal at such extreme range requires knowing the precise frequency at which to listen, which shifts constantly due to the Doppler effect as Voyager 1 moves. It requires accounting for the slight frequency changes caused by Earth's own motion. It requires pointing the antenna precisely enough to hold the beam for hours at a time. Commands sent back to Voyager 1 take over 21 hours to arrive. Responses take another 21 hours to return. Any interaction with the spacecraft involves nearly 2 days of waiting. Engineers plan every command sequence meticulously, knowing that a mistake cannot be corrected in real time. This is the reality of operating humanity's most distant, active spacecraft. A probe older than most people alive today, running on fading nuclear heat, transmitting whispers across a gulf that light takes most of a day to cross, still teaching us things we did not know about the universe. But the whisper is fading. The day when it falls silent is approaching faster than most people realize. Around 2025, the last science instrument aboard Voyager 1 will likely be shut down. The nuclear generators are producing less power each year, following the predictable curve of plutonium decay. At some point, the remaining power will fall below the threshold needed to keep any science instrument operational. The engineering team has already turned off several systems to extend the mission. Each deactivation has bought a little more time for the instruments still running. But the physics of radioactive decay does not negotiate. When the final instrument goes offline, Voyager 1 will still exist. It will still be moving outward at roughly 38,000 miles per hour, still on its trajectory toward the distant stars, still broadcasting a carrier signal that could theoretically be detected by the Deep Space Network antennas for years afterward. But the scientific data stream, the flow of measurements about cosmic rays, magnetic fields, and plasma conditions in interstellar space, will end. What humanity loses in that moment is difficult to overstate. No other spacecraft is currently en route to the interstellar medium. No mission is funded and launched to follow Voyager 1 into the space beyond the heliopause. The science community has discussed and proposed successor missions for decades, variously called the Interstellar Probe or similar names, with designs that would use modern instruments and a more powerful trajectory to reach the heliopause in roughly 15 years, rather than the 35 it took Voyager 1. As of the time the Voyager data is still arriving, no such mission has been funded and launched. The gap in data will be significant. Voyager 1's measurements of the interstellar medium represent one point in one direction at one moment in time. The interstellar medium is not uniform, and it is not static. Solar activity drives changes in the heliosphere that send pressure waves outward, and those waves interact with the heliopause boundary and the interstellar medium in ways that an operational instrument could measure over years. When Voyager 1 falls silent, that continuous monitoring ends. Scientists do have alternatives. IBEX and its successor mission IMAP, the Interstellar Mapping and Acceleration Probe, observe the boundary region indirectly through neutral atom detection from Earth orbit. Voyager 2 continues to operate in interstellar space from its different direction. But Voyager 2 faces the same power decay curve. It too will eventually go dark. There is also something less quantifiable at stake. Voyager 1 is the physical object humanity has sent furthest from its origin. A machine built by people carries encoded greetings from Earth on a golden record, moving through interstellar space at a speed that will take 73,000 years to reach the nearest star system. The end of scientific transmission does not end the journey. Voyager 1 will continue outward for billions of years, long after Earth itself has been absorbed by our aging star. In a meaningful sense, it is already humanity's most permanent artifact, the object most likely to outlast everything else we have ever made. But when the instruments fall quiet, something irreplaceable closes. And beyond where those instruments reached, a vastness begins that makes Voyager 1's entire journey feel like a single step. Voyager 1 has traveled farther from Earth than any human-made object in history. 14 billion miles, a distance so large that light takes over 21 hours to cross it. And in the context of our solar system, it has barely left the doorstep. The heliopause, which Voyager 1 crossed in 2012, sits at roughly the inner edge of the Oort cloud, the vast spherical shell of frozen bodies that forms the outermost gravitational boundary of our solar system. The Oort cloud is theorized to extend from roughly 2,000 astronomical units from our star, out to perhaps 100,000 astronomical units. 1 astronomical unit is the distance from Earth to our star, roughly 93 million miles. Voyager 1 has traveled approximately 160 astronomical units. The inner edge of the Oort cloud begins at approximately 2,000 astronomical units. Voyager 1 has covered roughly 8% of the distance to where the Oort cloud even begins. The outer edge of the Oort cloud sits at roughly 100,000 astronomical units. Voyager 1 has traveled roughly 0.16% of that distance. To put this in a form that is genuinely staggering, if the entire journey Voyager 1 has made since launch was scaled to the length of 1 foot, the outer edge of our solar system would sit roughly 600 feet away. Voyager 1 has taken one step across a 600-foot room. The region between the heliopause and the Oort cloud is essentially unmeasured. No instrument has ever operated there. It is a zone of interstellar space that is part of our solar system's gravitational domain. Objects out there orbit our star, but is physically filled with interstellar medium conditions similar to what Voyager 1 is currently measuring. It is neither the clearly heliospheric space of the inner solar system, nor the deep interstellar space that will exist beyond the Oort cloud. The travel time to the inner Oort cloud at Voyager 1 speed is roughly 300 years. To reach the outer edge would take approximately 30,000 years. The nearest star system, Alpha Centauri, sits roughly 4.25 light-years away. At Voyager 1's current speed, reaching it, if the probe were aimed that direction, would take roughly 73,000 years. These are not numbers to recite. They are dimensions of a reality in which human exploration, as currently practiced, has barely begun. Every model of the Oort cloud, every prediction about what lies between the heliopause and the stars, is built from indirect evidence and theoretical inference. No direct measurement exists. The data gap between where Voyager 1 operates and where any future probe might eventually reach is measured in centuries of travel time. The universe beyond Voyager 1 is real. It is structured. It contains objects, fields, and phenomena that will change our understanding of the solar system when we can finally measure them. And the first of those unmeasured structures, the Oort cloud itself, is one of the strangest places our solar system contains. The Oort cloud has never been directly observed. Every image ever taken by every telescope ever built has failed to photograph a single confirmed Oort cloud object in place. The distances involved make direct observation essentially impossible with current technology. The objects are too small, too dark, and too far away for any existing instrument to resolve. And yet the Oort cloud's existence is about as well established as any unobserved structure in science. The evidence for it comes from the behavior of comets. Long-period comets are comets with orbital periods exceeding 200 years, some with orbits taking millions of years to complete. When astronomers track where these comets come from, meaning what part of the sky they appear to fall toward our star from, the answer is revealing. They come from every direction with roughly equal frequency, and their orbital parameters, when calculated backward to find the origin of each comet's trajectory, point to distances of tens of thousands of astronomical units from our star. A Dutch astronomer named Jan Oort proposed in 1950 that a vast spherical cloud of frozen bodies must surround our solar system at these enormous distances, acting as a reservoir from which long-period comets are occasionally disturbed and sent falling inward. The proposal explained the observed comet distribution precisely. Subsequent calculations have confirmed the basic model repeatedly. The Oort cloud is estimated to contain trillions of icy bodies, ranging from small chunks to objects potentially hundreds of miles across. Their combined mass might equal or slightly exceed Earth's mass, though estimates vary widely. The objects are too widely spaced to interact with each other under normal circumstances. The average Oort cloud object is separated from its nearest neighbor by enormous distances. What disturbs Oort cloud objects and sends them toward the inner solar system? Several mechanisms. The gravitational tug of passing stars, which approach within a fraction of a light year of our solar system on timescales of millions of years, nudge Oort cloud objects onto new trajectories. The gravitational tide of the Milky Way galaxy itself, the combined pull of billions of stars and dark matter in the galactic plane, exerts a periodic force on the outer solar system that can dislodge objects. Molecular clouds that our solar system passes through during its galactic orbit can gravitationally perturb the entire Oort cloud population. Each of these mechanisms sends a small fraction of Oort cloud objects tumbling inward. Some reach the inner solar system and become the long-period comets we observe. Most are ejected from the solar system entirely on hyperbolic trajectories, becoming interstellar wanderers. And here is the connection that makes the Oort cloud scientifically urgent beyond its own properties. The same interstellar medium that Voyager 1 measured just outside the heliopause fills the space throughout the Oort cloud. The galactic cosmic rays, the magnetic field, the neutral atom flux, all the conditions Voyager 1 detected at the heliopause are present throughout that vast spherical shell. The Oort cloud objects themselves have been soaking in that environment for 4.5 billion years. Their surfaces are chemically altered by cosmic ray bombardment in ways that inner solar system objects are not. They carry a record of interstellar medium exposure that, if we could ever retrieve and analyze it, would provide an independent measure of conditions in our galactic neighborhood over geological timescales. Voyager 1 cannot reach them. Nothing we have built can, yet. But they sit there. Trillions of frozen witnesses to the environment Voyager 1 was the first machine to ever directly measure. The popular story of Voyager 1's achievement focuses on the heliopause crossing, the moment when a human-made object entered interstellar space for the first time. It is a genuine milestone, confirmed by data, celebrated by scientists who dedicated careers to the mission. But the milestone requires context to be properly understood. The heliopause marks where the solar wind stops dominating the particle environment. It does not mark the gravitational edge of our solar system. Gravitationally, our star's influence extends far beyond the heliopause, holding the Oort cloud in orbit at distances thousands of times greater. In the gravitational sense, Voyager 1 has barely left our solar system at all. The distinction matters because the word edge means different things depending on which physical property you use to define it. Particle environment edge. The heliopause confirmed at roughly 100 to 130 astronomical units in the directions the Voyager probes traveled. Voyager 1 crossed this. Gravitational edge, the point where our star's gravity becomes weaker than the gravitational influence of nearby stars. This sits at roughly 100,000 astronomical units or more, in the deep Oort cloud and beyond. Voyager 1 has covered less than 0.2% of this distance. The difference between these two definitions is not a technicality. The vast region between the heliopause and the gravitational edge is filled with real objects, real fields, real phenomena that science has never measured directly. It is not empty. The interstellar medium, Voyager 1, samples continues throughout that region. Oort cloud objects orbit throughout it. The local interstellar magnetic field runs through it. Future science in this region would be transformative. A mission reaching the inner Oort cloud, roughly 2,000 astronomical units from our star, would encounter objects untouched by the planetary formation processes of the inner solar system. It would measure interstellar medium conditions with modern instruments orders of magnitude more sensitive than Voyager 1's 1970s technology. It would test models of the heliosphere's shape and the Oort cloud's structure with direct observation rather than inference. Scientists have proposed exactly such a mission. The interstellar probe concept, studied in detail by NASA over multiple years, envisioned a spacecraft launched on a fast trajectory reaching the heliopause in roughly 15 years and pushing outward to 1,000 astronomical units and beyond over a 50-year mission lifetime. The scientific return would dwarf Voyager's already extraordinary contribution. The mission has not been funded. The science case is overwhelming. The Voyager data made that clear by demonstrating how wrong our pre-measurement models were and how rich the real boundary region turned out to be. Every surprise Voyager 1 delivered suggests that the region beyond it, unmeasured and full of structure, will deliver surprises of similar magnitude. Voyager 1 opened a door. It stepped through and looked around in one small patch of the room. The rest of the room, the vast interstellar neighborhood our solar system actually inhabits, remains in the dark. The doorstep achievement is real, extraordinary, historic, and the journey it represents is, by the scale of what remains unmeasured, a single step. Before Voyager 1, the space beyond our solar system was a theoretical object. Scientists had models, equations, predictions built on assumptions, extrapolations and indirect evidence gathered from the inner solar system and from observations of distant stars and interstellar clouds. The heliosphere, the termination shock, the heliopause, all existed as mathematical constructs, real in principle, but untested against actual measurement. Every single major feature of the outer heliosphere and near interstellar space turned out to be different from those predictions in ways that mattered. The heliosheath was thicker than calculated, revealing a pressure imbalance between the solar system and its environment that shifted density models for our galactic neighborhood. The termination shock accelerated particles less efficiently than predicted, requiring new physics of shock processes at our specific scale. The heliopause crossing confirmed the first direct measurement of interstellar medium plasma density, which came in roughly 40 times higher than standard models suggested. The interstellar magnetic field ran at an angle that required accounting for the magnetic legacy of supernovas, millions of years old. The bow shock predicted by decades of theoretical work turned out not to exist. The ribbon of energetic neutral atoms, mapped by IBEX, generated by the same boundary Voyager 1 crossed, remains only partially explained. Every surprise was productive. Each wrong prediction identified a gap in understanding that subsequent work filled with better physics. The models that exist today for the heliosphere, the local interstellar medium, and our solar system's interaction with the galaxy are more accurate, more detailed, and more grounded in reality than anything that existed before Voyager 1 returned data from the boundary. That is the specific, irreplaceable contribution, not just going far, but measuring something real and delivering the kind of information that forces understanding to grow. The data also reframed humanity's position in the galaxy in a concrete way. Our solar system is not a self-contained island. It is a dynamic structure embedded in an interstellar environment that actively shapes it, compresses it, exchanges particles with it, and carries the magnetic and chemical signatures of violent events from millions of years in the past. The heliosphere is a boundary, but a permeable one. The galaxy reaches inward through it continuously. Earth sits inside a nested system of shields and influences, extending from its own magnetic field outward through the heliosphere and into the surrounding interstellar cloud. Understanding that system in full is one of the foundational scientific projects of the coming centuries. It requires knowing conditions at scales from Earth's magnetosphere out to the Oort cloud and beyond. Voyager 1 measured 1 point in one direction at one moment. It was the first measurement. The picture it started is far from complete. The golden record on board carries sounds from a world that has changed enormously since 1977. The machine carrying it has outlasted the careers of most of the engineers who built it. Its signal, still crossing 14 billion miles every 21 hours, will eventually fade. But what it told us about where we live in the universe, what surrounds us, what shapes us, what we are embedded in, that does not fade. The edge of our solar system is stranger, more dynamic, more connected to the rest of the galaxy, and more consequential for life on Earth than anyone imagined when a rocket lifted off from Cape Canaveral in the autumn of 1977. Voyager 1 went to the edge, looked outward, and what it saw changed everything we thought we knew about home.